Special relativity theory is a physics theory describing the dynamics of objects moving at near light speeds relative to each other. Because the objects are moving so fast, the effects of SRT cannot be observed in real life by students. Here, multimedia and VR simulations enable the visualization of these effects, such as length contraction and time dilation, by manipulating the flow of time, and in so doing facilitates student learning. For example, we can say that this object is traveling at 99% the speed of light, but we are seeing it in extremely slow motion. Many existing multimedia and VR simulations are in the sandbox style. These have the advantage of having higher levels of learner autonomy, but come at the cost of having reduced structure. We instead design a tutorial-style VR simulation that integrates structured guidance with explicit visualization of relativistic effects. With Einstein serving as the narrator, students are guided through a structured but interactive module that teaches them about the resolution of the barn-ladder paradox, a classic paradox in the theory of special relativity. To study the efficacy of our simulation for teaching special relativity, we ran a mixed method study with 28 undergraduate students from an introductory physics course at Cornell University, most of whom have little prior knowledge of the theory. Each participant completed a pre- and post-test comprising 13 questions from a validated relativity concept inventory, as well as a semi-structured interview. Quantitative analysis revealed that students achieve a statistically significant improvement in their understanding of special relativity through the simulation, especially for the concepts of frames of reference and length contraction. Additionally, the interview uncovered a number of design principles for tutorial-style simulations, which include showing visualizations of the same event from multiple perspectives, providing both audio and visual information at the same time, and providing students with the means to personally control the pacing of the simulation. It was also found that students thought about space and time differently, despite there being clear parallels between the two concepts, and that they often attempted to use existing classical physics knowledge to make sense of special relativity, despite the fact that classical physics concepts do not apply in the new context. These findings further contribute to understanding the way students reason about the theory. In all, our study reveals that tutorial-style VR simulations can serve as an effective teaching resource for special relativity theory and highlights potential for further investigation.